Okay, so hi everybody and welcome to this week's Earth Science Research Group seminar. Before we get started, I just wanted to remind everybody about the schedule that we've got over the next few weeks, and we'll drop a link to a Google Doc where you can check out all the talks that are coming up and all the links to YouTube and things like that. All the talks are on Wednesdays, but they're at slightly different times to sort of take into account that people might be joining at different time zones, things like that. So it's always on Wednesdays, but check the schedule just to find out what time it is. And so I will hand over to Caitlin Shaw, who's going to introduce our speaker today.
Yeah, hi everyone. So today we're really happy to have Dr. Jenny Wong with us, who is a postdoc at the Institute of Earth Sciences at the University of Grenoble. Jenny's background is in maths, which she studied for her undergrad degree at the University of Leeds. And she stayed in Leeds to complete her PhD at the Centre for Doctoral Training in Fluid Dynamics, where her work focused on the fluid dynamics of the Earth's deep interior. And following her PhD, Jenny moved to France for her first postdoc at the Institute of Earth Physics in the University of Paris, where she continued to develop her research of the dynamics of deep Earth. And today, Jenny's going to present her work on modelling the base of the Earth's outer core as a slurry. So yeah, thanks, and over to you, Jenny.
Thank you for the introduction, Caitlin, and thank you for organising this and having me here. So yeah, it's a pleasure to present this work to you today, and it's about a regime diagram of the slurry Effleur at the bottom of the Earth's core. So the first thing that you might be thinking of is, if I change my slide, what is the Effleur? So in order to explain this, I'm going to take you on a deep dive of the interior of the Earth. So if I take a planet-sized knife and cut it in half, what you will see is a solid inner core, a liquid outer core, and then a viscous rocky mantle. And then here we are on the surface of the Earth. And the liquid outer core is actually composed of solid iron, which is alloyed with a lighter material. And this detail will be important later. And we've actually known the structure of the Earth for, I'd say, quite a while now. There's this interesting classification of the different layers of the Earth, which was tabulated by Bullen back in 1953. And what he did was label the surface of the Earth layer A and then progressively down to layer G, which denotes the inner core. And you might notice here that there's a bit of a transition layer between the outer and the inner core, which Bullen called layer F or shell F. So this was found quite some time ago, but actually this is possibly a fake Effleur, because what happened 20 years later is some seismologists called Cleary, Haddon, King et al. They actually debunked this early Effleur and actually found it was an artifact of some seismic waves scattered from the D double prime layer. So the interest in this initial Effleur completely disappeared after that. And even though some people tried to start thinking about dynamical models for how to explain it, but this was kind of like the death knell for interest in the Effleur for quite some time. And then in 1981, Ziavonsky et al. Published this Prem model, which is basically the standard reference model that we have for the 1D interior of the Earth. So here we have the P wave velocity that you would see from seismology, and this is a function of radius. So P waves travel quite quickly through solid as we're traveling through the solid inner core. And then at this inner core boundary, we transfer to this sort of steady decrease in the P wave velocity as the waves travel through liquid. And what this model does is that it assumes that the outer core is adiabatically stratified throughout. So it's this profile is consistent with this assumption. But following this model 10 years later, there was a study published by Surio and Pupinier, who actually saw something that contrasted with this Prem model, in which they observed a slowdown in the P wave velocity in the bottom of the outer core. And what this means is that the density in this layer at the bottom of the core is much more denser than you would expect. And this departure from this adiabatic assumption here that is given by Prem means that this layer can't be explained by adiabatic compression alone. And following this study, there have been many other seismic observations that point to a slowdown in the P wave velocity in this region. And many layer thicknesses are expected to be between 150 to 400 kilometers. So what does this really tell us about the density structure in this F layer? So here's a corresponding cartoon. Instead of the P wave velocity, we're looking at the density now, which pretty much follows what you would expect with from the seismic observations, because they're both related. The P wave velocity is roughly inversely proportional to the density. So here you get a really dense inner core, and then again you see this drop in the density before it follows this decline, which agrees with this adiabatic assumption from Prem. And then this dashed line here would be what would correspond, this would be what would correspond to the more recent observations of the slowdown in the P wave velocity. So this is kind of a sketch of what density might infer from these seismic observations. There are also two other measurements that seismologists can take, which is the, or can calculate, is the inner core boundary density jump derived from normal mode data, and derived from another set of data called body waves. And so normal modes are waves that have a really long resolution length, on the order of about 100 kilometers. And so the inner core boundary density jump derived from this represents the difference between the average densities between the bottom of the outer core and the top of the inner core. Whereas the estimates from body wave data have a much shorter resolution length scale, and they represent the actual density difference either side of the interface itself. So the difference between these two values actually really indicate the existence of a stably stratified layer. And so why are we sort of so concerned with the existence of this layer? And one of the reasons is because the presence of this F layer could be linked to the geodynamo process that generates the Earth's magnetic field. And so the convective motion of the liquid iron core is powered by the heat that's extracted from the core mantle boundary here. And so this leads to the freezing of the solid inner core from the center of the Earth, because the melting curve is steeper than the adiabat. And this freezing releases latent heat and light elements into the liquid. And these light elements can drive compositional convection in the core. And this is thought to be the main power source for the dynamo in the present day. So the key issue that I'm concerned about is how can light elements pass through a stably stratified F layer and out into the bulk of the liquid outer core that's convecting. So a first guess might be, oh, is this layer a thermally, this layer a thermal boundary layer? But in terms of the thicknesses that are observed from seismology, they're on length scales that are much higher than the diffusive length scale. So it kind of rules out that it could be a thermal boundary layer. So there are some other possible scenarios. that people have hypothesized over the previous years. So this first scenario is a thermochemical layer on the liquidus, first proposed by Gubbins et al. In 2008. And then what they propose is that we have this layer that takes into account temperature and compositional changes. And what they do is they assume the temperature is always following the liquidus temperature, which is the temperature that divides the solid from liquid phase. And this temperature depends on pressure and also depends on light element concentration. But what they did was they fixed the compositional gradient here, so to match up with what was given by the seismology. So other alternative models were proposed. Another model is a convective translation model, in which melting and freezing is happening simultaneously at the inner core surface. So you have melting on the eastern hemisphere, which releases a rich, dense liquid that coats the inner core, and therefore giving this stable stratification. My hypothesis is that we have a slurry scenario happening in the Effleur. And this was originally, the theory for this was originally posited by Loper and Roberts back in 1977. And what this scenario is that I focus on is a two-component, two-phase system. So what I'm considering in terms of the constituents are iron and oxygen that composes the core material. And also I'm considering phase change between solid and liquid. So we have crystals of solid freezing out from the liquid alloy, which happens above the inner core boundary, and they fall under gravity towards the inner core in order to grow it. So we have this distributed release of light liquid oxygen, while a heavy solid iron builds up the Effleur. So this is a really cool way of explaining how solid can provide a pathway for light elements to be transferred through the Effleur. And one key assumption of this model is that the solid fraction overall is quite small. So we're dealing with very small particles of crystals in this setup. For all of the gory details, you can head over to the paper that I published 3 years ago now in GGI. But I'm just going to give you a quick overview of what goes into the model. So I solve some governing equations. So the main one is the liquidus constraint, which kind of makes things quite different to what you might assume from, say, a thermochemical system. But this is assuming that we're on that the solid and liquid are in phase equilibrium, which is similar to the Gubbins scenario. So it constrains us to the liquidus temperature throughout the layer. I also conserve oxygen in the layer. So this describes the transport of oxygen and it's not created or destroyed. And also I conserve energy too. So this is all thermodynamically self-consistent in this model. And the equations are quite complicated. So what I've done as a first step is to assume that I have a steady system. I'm in 1D and I'm solving these equations in a spherical geometry. And what's happening in my model is I have a growing inner core. So I solve this system in a moving reference frame that's moving at the same speed as the inner core growth rate. And this growth rate is also determined from my calculations too. It's not a fixed parameter, it's actually calculated as well. And just going through the boundary conditions that I impose on this system. what I do is I fix the oxygen concentration at the top of the layer, which is from other studies maybe estimated to be about 8 mol%. I also constrain the temperature at the top of the layer to be the liquidus temperature obtained from other sources like mineral physics experiments. I also say that the flux of solid vanishes at the top of the layer. And in order to do this, I invoke a mixing sublayer at the top of the layer, which is caused by the difference in velocities between a steady slurry and a vigorously convecting outer core. Also, the solid flux at the base of the layer has to be proportional to the speed of inner core growth. So that's how that is fixed. And then I have two real sort of unknown parameters here, which are the heat fluxes that coming through the inner core boundary and through the what I term the core slurry boundary. So the heat fluxes through the bottom and the top of the layer are really unconstrained and are parameters to be varied within my study. So what I've done is like convert these equations into a dimensionless system. So the parameters that I'm really interested in looking at in the results that I'm going to present you are the Péclet number, which basically corresponds to the amount of heat flux coming through the bottom. The Stefan number, which is controlling the amount of heat that comes out the top. And then also I vary the Lewis number, which is basically changing the thermal conductivity of the system, because there's kind of two different groups that believe that thermal conductivity of the core is actually quite low, so something around like 30 watts per meter per Kelvin. And then there's another group that believe that it's quite high, on the order of 100 watts per meter per Kelvin. So I'm just going to look at those two end member cases. So while I'm solving these equations, I'm always kind of bearing in mind that there are some independent geophysical constraints which I want to my solutions to agree with. So I mentioned the ICB density jump derived from normal mode data at the beginning of the talk. So these values can range between 600 and 1,000 kilograms per meter cubed. And then the estimates derived from body wave data can vary even more. And the least such value is 280, and the highest can be as big as 1,100 kilograms per meter cubed. There's also some constraints on the core heat flow overall. And this is constrained by the overlying mantle, as I mentioned earlier. So the maximal value is 15 terawatts and the minimum is 5. And there's maybe some tentative estimates on what the ICB heat flow is, but it's really not that very well constrained. But physically, it has to be greater than 0. And there is an estimate from Pozzo et al. Of about 2 terawatts. So this is what you get when you solve the equations. So here is the temperature profile as a function of radius. So you can see that it's decreasing because it's hotter in the center than outside in the outer region. Then you've got the oxygen profile. So it increases to the fixed value at the top of the layer. You've got the solid flux, which is negative down towards the inner core, and it vanishes at the top of the layer. And then taking all of these contributions to the density using an equation of state, here is the corresponding density profile as a function of radius. So you can see here I've plotted the density that's derived from Prem, and you can see that it's higher than what we expect from Prem, which corresponds to a stably stratified Effleur. So that's good news. One of the features you can see is the effect of the liquidus constraint, because it's the gradients of the temperature and oxygen are locked together. And yep, I mentioned that the solid flux is negative downwards, and here are progressively thicker Effleurs. So The first line was for 150 kilometers thick, and I vary this until 400 kilometers. And what you can see with the densities is that increasing the layer thickness destabilizes the layer, because now you can see that it's actually dipping below the Prem value. So taking a closer look at this, I've separated out the density perturbations. So this is not the total density, it's the perturbation to the reference density, which I've taken to be hydrostatic. So for a layer 150 kilometers thick, you can see that I have a stable layer because the density perturbations are negative. And then for a layer 400 kilometers thick, you can see that in the mid depths, there are positive perturbations, which indicates that we have some destabilization happening here. And this is because the pressure part of the liquidus relation begins to outweigh the temperature part, the compositional part, because the liquidus, you might remember when I mentioned earlier, the liquidus depends on the pressure and the composition. And these extra lines tell you the individual contributions from the temperature, oxygen, and solid perturbations. So you can see that the oxygen is mainly the responsible driver for the stable configuration, or whether it's stable or unstable. And temperature is always going to be destabilizing, but whether what competes to win out to give a stable layer can be quite complicated to tease out. So moving on to just the regime diagram in general, which is the point of my work, it's to solve these equations many times over a large parameter space. So what I've done is vary the Péclet number between 0 and 2500, and vary the Stefan number between 0 and 3. And then I've chosen the high Lewis number case. So what you'll find is that as you increase the Stefan number, you'll go from no slurry to slurry. And this is because the Stefan number measures the ratio between the heat flows out of the top of the layer and the bottom of the layer. So if you have more heat flow coming out of the top than what's coming in at the bottom, then you're not going to have a slurry. So that's this interesting result here. And then following that, you can divide this solution space into two, where you have unstable and stable configurations. And this is determined from looking at the density perturbations like I showed you in the slide before. And this occurs when the Péclet number exceeds the Lewis number, roughly. And this is basically when the rate of advection from the compacting layer as the inner core is growing overcomes the thermal diffusion rate. And then overlaying the stable region, I've put in contours of the CMB heat flow, because that's one of the constraints that I want to be mindful of. So you can see where these are all solutions that I will discard as not geophysically relevant because the total CMB heat flow is below 5. And similarly here, all of these solutions are above 17 terawatts. So we have a decent amount of solutions that agree with a stable, stably stratified Effleur that is consistent with this constraint on the CMB heat flow. Additionally, I've done a same thing with looking at the density jump across the layer. So this is the difference in densities between the top and the bottom of the layer. And in this case, in the high Lewis number case, we have density jumps that are roughly around 100 kilograms per meter cubed. And then in the low Lewis number case, in terms of the density, you can see that you have a larger density jumps, which kind of increase more as you increase the Péclet number. And you have the same boundary here, where once the Péclet number exceeds the Lewis number, you encounter the region of stable slurry stably stratified slurries. Yeah, so using the results of this regime diagram, what can this tell us? Interesting about, say, the seismic density jump. So, for example, if I take the largest, the bounds on the density jumps that I get from the high and low Lewis number cases, then they are greater than 80 kilograms per meter cubed in the high Lewis number case and greater than 100. So this is telling me the difference in the densities between the top and the bottom of the layer. And then assuming I know a value for the normal mode data, say it's 600 from Prem, then this allows me to estimate the value of delta rho from the body wave data. So I have bounds in which for the high Lewis number case, delta rho bod should be less than 520. And for the low Lewis number case, it's 500. So compare this with what we know from the observations. This, I mentioned earlier, this ranges quite largely between 280 and 1,100. So what my model is saying is that we might expect, if we assume the layer is composed of a slurry, body wave density jumps that are on the lower end of this range rather than the higher end. Also from my slurry model, I'm able to determine the density everywhere in the layer. So assuming that I have some bulk modulus, then I can determine the P wave speed from my density profiles and compare this with what we get from the other seismic models. So here is a plot of the P wave speed from Prem and another reference model called AK135. And then this yellow line denotes an observation by Otaki et al. 2015, which sees this slowdown in the P wave velocity that infers a stably stratified layer. And so what I've done is chosen some parameters that fit within this profile. However, there is a pretty good fit, but the boundary conditions are slightly different because what I've assumed is that the density needs to be continuous with Prem at the top of the layer. But all in all, the difference between the slurry and Otaki's profile is about 0.1%. But the interesting thing, this is more of like a proof of concept, is that if we could improve our seismic observations, then it might be, and with maybe a few adjustments with the slurry model, it might be a way of narrowing down what parameters I need to get a stable slurry and tell us something about the heat flows, for example, or what thermal conductivities might be consistent with those seismic observations. So so in summary, from listening to my talk, hopefully you now know that there is a consensus in a slowdown of the P wave velocity at the bottom of the liquid outer core. That a slurry could provide an explanation of how a stably stratified F layer can exist. If you construct a regime diagram that you can show that a stable slurry is likely when a Péclet number exceeds the Lewis number, and this also agrees well with geophysical constraints. The model also suggests that there is an upper bound on the on the inner core boundary density jump from body wave data that is less than 520 kilograms per meter cubed. And an interesting avenue for further investigation could be, can we further elucidate conditions of the slurry F layer with improving seismic observations? And what impact does a stably stratified F layer have on core dynamics overall and the resulting field morphology of the geomagnetic field, which is the subject of the work that I did in IPGP Paris. So if you want to know more about the regime diagram, I invite you to have a look at my paper, or yeah, you can also ask me questions as well. And thank you for listening. And I'm looking forward to taking some questions.
Oh, thanks for a great talk, Jenny.
Thank you, Caitlin.
Yeah, do we have some questions for Jenny?
I have a question, if that's okay.
Yeah.
Hi, Jenny. That was a really nice talk. I have to run like nearly immediately, but I'm just going to get in a quick question, if that's okay.
Okay.
So I just wondered, I mean, you're being quite cautious with what you're saying at the moment, but it looked as though from your regime diagram that the low conductivity case gave you a bit more freedom to match the observations as they exist. Do you have any sort of vague, kind of a general preference towards the low or high conductivity case?
With respect to the density jump from body wave data, I don't think there is a great deal of difference when you use, sorry, if I bring up the slide with the table that compares the values, which I have, oh no, where did it go? Was it here? Oh no, that's the summary. Oh, okay, I have too many animations, so it's got lost in me. Here's the table, here we go. The values that I get when it comes to this particular observation, it doesn't really change the bounds much. Like there's a difference of about 20. So in terms of the influence of the thermal conductivity in this regard, there's not really much. But this is a bound, however. It's so I don't know, there are many like solutions to the slurry scenario that fits with these constraints. So it's difficult to pinpoint which one's like the solution with, the perfect parameter values, but this is as much as I can say when it comes to trying to say something about these seismic observations. I can only really provide bounds. I don't think I can really say, okay, this is the parameter set that gives me something that matches completely with the seismology. The influence, I mean, you can see in the regime diagram, yeah, indeed, that there is a lot of, there is a big change in what kind of density jumps that you achieve through changing the Lewis number, aka the thermal conductivity.
Great, thanks very much.
Okay, thank you.
I have a question, Jenny, which was, you mentioned I think, increasing the thickness destabilizes the layer, which is shown by the density variations. I think I just didn't fully understand. Like, could you tell me a bit more, please?
Yeah, sure. So yeah, you can see quite clearly as I've changed the layer thicknesses, you can see that these density profiles become less and less. And what I tried to do here was to kind of extract that information in terms of the actual density perturbations rather than the total density, because the background profile is always going to be I've taken as a hydrostatic reference. And then what's actually destabilizing or stabilizing the layer is actually the perturbations to that reference profile. And so I don't know if I can really say what's responsible, because it's a mix of what dominates. So like you can see, okay, the difference in the density perturbations between the smaller layer thickness and the larger layer thickness. And then here in this graph, what I've done is separate those contributions from the temperature, oxygen, and solid fraction perturbations. And there's just, it depends on the competition between oxygen and temperature, essentially. I think the influence of the solid perturbations are not quite significant, and I think that's probably because overall there's not much solid in a slurry layer. But it's related to this liquidus constraint in which there is this relationship in which there is a balance to be had between the effects of oxygen and temperature. So there is more to be done. I think like it'd be nice to kind of do a separate parameter study for the layer thicknesses. But what I've done is kind of look more on the side of, in my parameter study, I've not actually looked at the different layer thicknesses. It's more focused towards the heat flows in and out of the layer, which are probably even less well constrained. But yeah, like it would be really good to kind of really pinpoint in the balances that control what gives rise to a stable or an unstable layer. So it's a good question.
Thanks for answering. Janine has her hand up.
Virtual hand. I really enjoyed your talk, Jenny. I think you probably made what's a very complicated model quite relatively understandable for a non-expert. So thank you for that. I guess I was wondering like, how applicable your model would be to other terrestrial planets, either now or like in the past, and like I just wondered about that.
Yeah, that's a really good question. And yeah, it is actually quite applicable to many different planetary bodies. It's also, this model specifically has been applied to Mars, because at some point in Mars's history, there was a magnetic field. And so this is one way, it's called iron snow because I use the term slurry, but people who do planetary sciences use the term iron snow. And this is one way of providing the energy to drive a dynamo. And in the case for Mars, it's been applied there. And there's also similar ideas for Ganymede, for example. And in general, I think for me, it's really important to study two-phase flows when it comes to modeling planetary interiors, because we have a solid inner core and we have a liquid, so there is phase change happening, and they're not really taken into account in a lot of models for dynamo processes. But actually, there is it's the subjective investigation that I'm doing myself. But yeah, it's a physical process that's there, and it's got, I think, more recently more and more interest. Like stably stratified regions can be found in general. I think there's also a group that also looks at a stably stratified layer in Mercury as well, for example. So there are a lot of applications.
That's great, thank you.
Thank you.
This is kind of related to what Janine asked, but could there be a slurry in other locations within the Earth?
Yeah, so a lot of there's more kind of industrial applications too. I think there are models of slurry crystallization in iron casting processes, for example, in metallurgy. Also, there's maybe not the present day Earth, but when it comes to the early Earth, when we had this magma ocean in which the mantle has crystallized from, that crystallization process can also be modeled as a slurry also. So yeah, it's a fascinating subject, and it's also something I've kind of looked at. My research right now concerns core mantle differentiation in planetesimals. So in the early evolution of planetary bodies, when everything is a big solid mix of metal and rock, there's also applications there in terms of how the core can sink out of a light silicate mantle too.
Oh, cool.
I think there's also possibly, I mean, with magma chambers also, that's kind of related to what you do, right? Maybe perhaps not a slurry type scenario, but there's also if you assume a higher solid fraction, I think there's been some mushy type models of magma chambers too. So, you know, phase change is important. It happens.
Yeah. Are there any further questions for Jenny?
Can I just ask a methods question, Jenny? That was a really good talk, but I don't really know much about the deep Earth, but I do a lot of modeling of Earth surface processes and use, you know, similar kind of plots where we try to summarize the results from lots and lots of different models. But, you know, I'm always a bit unsure what to actually call those plots. So you called it a regime diagram, and I think that's because you separated it out into the various different sort of zones of behavior.
Yeah.
But more generally, are these plots referred to as parameter space plots or solutions?
Yeah.
Okay.
Yeah, it's the same thing. Yeah. So like what you're seeing in this diagram, like each little pixel in these contour plots represents like a one simulation, one solution. Yeah. And then I categorize those solutions into these different spaces. Yeah.
Okay, so if you didn't categorize it into the different regimes, would you call it then a parameter space plot? Is that the correct term?
I don't know what parameter space plot would really mean. So I don't know in terms of the lexicon. I'm not entirely sure.
What would you call it then if you didn't do the regime classification? Do you think?
I don't know. Like this is for me like because I have a mathematical background. This is quite a common thing in maths to like say with double diffusive convection, you can construct a regime diagram to tell you you have slot fingers and symmetry. It's a similar idea to that.
Oh, okay. So I mean, I'm asking because I don't know the answer. It's not like a trick question or anything. I've just never really known what to call these diagrams. So I just
I have a feeling it's the same. It's a similar thing. It's the same thing. Yeah.
Right. So if I call it a regime diagram, then mathematical modelers are not going to. They're going to know what I mean.
Yeah, I think it has a significant. I think it has a meaning to like mathematical modelers for sure. Yeah.
Cool. All right. Thank you. That's really helpful. Thanks.
You're welcome.
Okay, well, yeah, if there are no more questions, I think we'll leave it there. So thanks again, Jenny. We're going to be heading over to the Herdman Gather Town now, so you're all welcome to join us for continued discussion about this and anything